Now we're going to discuss section 3 of chapter 10. Section 3 is about matched samples as opposed to independent random samples that we discussed in the previous videos. In matched samples, what we have are two samples taken from the same sample subjects. Observation 1 is made prior to an event from a sample subject, and observation 2 is made from the same subjects as sample 1 after a given event. For example, suppose if you want to test the efficacy of, say, a diet program, so you may want to weigh each subject before they go into the program, and then match each observation with the weight after the completion of the program. So this is the reason why this is called match sample, because each observation is matched to another observation from the other sample. So an observation in one sample is matched to a corresponding observation in a second sample. For this reason, the two samples will have to be of the same size, because for each observation in one sample, you must have a corresponding observation in the other sample. And that's why it is called match sample. So when you have a match sample, the sample sizes are equal, okay, n for sample 1, n for sample 2. Then we have one observation, let's call that x sub 1I, it's the ith observation from sample 1. Then we have x sub 2I, so the ith observation in sample 2. And these two are matched, these two are taken from the same subject, same sample subject. So then we can define a sample difference between the two sample observations. So x sub 1I minus x sub 2I is the difference, the ith difference in the samples. So in this way, we can convert the matched samples into one single sample of differences. So originally we have two samples which are matched, and now we have reduced it to a single sample of difference, and we define mu sub d as the average of those differences. Then sigma sub d is the standard deviation of those population of differences, and we can compute a sample mean of the differences, sum all the differences, divide by n, and we can compute sample standard deviation of the differences. So instead of x, we use the d's. So now we essentially have a single population case. Instead of x, we have d. So confidence interval will be, instead of x bar, we have d bar, and then the t-table value, s sub d over square root of n, the degrees of freedom equal to n minus 1. And the hypothesis testing is going to be similar to the single population hypothesis testing, the three types of hypothesis, and the test statistic will be t d bar minus mu sub 0 over standard error of d. And then we will have the two t distribution or t functions for the p-value, the degrees of freedom being equal to n minus 1. We'll use the Excel data analysis command for match samples to generate all of this information. Now we're going to look at what is called match sample. Match sample is very useful, helpful if the samples taken from the two populations. So remember, we are talking about estimating inference about the population mean of two different populations, and if the samples taken from the two populations also contribute to the difference in the values that we are measuring, then the differences in the samples may conflate or may conceal the actual difference in the actual difference attributable to the differences in the population. So when that is the case, then we take the same sample subjects and measure them once for the first population characteristics and measure them once for the second population characteristics and take the difference. So for example here, suppose we want to test whether two different production methodologies, are they equal or are there any differences in productivity of the two different methodologies. Now we know that depending upon the experience and skill level of workers, the productivity may be different for different workers. So if we have the worker bias in the samples in the two different populations, then we end up hiding the difference of that's attributable to the actual method. So we take a random sample of say 6 or whatever number of workers, and they are trained, each worker is trained in the two different methods. Then each worker works with the first method, and then we measure how long it takes to complete the task, record that. And the worker works in the second method, and we record how long it takes for the second method. And we can even randomize the sequencing. Some workers will go method 1 first and then method 2, and some workers will go method 2 first and then method 1. So method 1 data is here, method 2 data is here, and then we convert these two samples into a single sample by taking the difference. Say 6 minus 5.4, 5 minus 5.2, and then we work with the differences. And we can develop confidence interval, we can do hypothesis testing for the difference. So let's first identify or describe the populations and the parameters and so on. So here we have two populations. The first one is task completion time in minutes for method 1. The second one is the task completion time for method 2, and we take the difference between the two, d sub I, as x sub 1 minus x sub 2. So now we can do that here. We take x sub 1, the method 1, minus method 2. Okay. So now we have difference. This is a small example, but we could have, instead of 6, we have 60 workers, 100 workers, doesn't matter. We follow the same procedure. So now we have a sample of differences. Now we'll do all the computations for the differences. So here mu sub d becomes our parameter of interest, where mu sub d is mu sub 1 minus mu sub 2, which is the difference or the average of the difference in task completion times between method 1 and method 2. Okay. So now we can set up the sample statistics. Sample size is count of that. Then sample mean is average of these differences. Okay. And sample standard deviation is stdev.s of these differences. So now we have all the sample statistics that we need. Now standard error of estimate, now remember, now it becomes one population of differences and a sample taken from that one single population. So all the single population formulas, like in chapter 9, will hold here. So we take S over square root of n will give you the standard error. Okay. Now degrees of freedom is n minus 1. We want confidence interval. So suppose we want confidence interval for 95%. So 1 minus alpha is 95%, so alpha is 1 minus that. And then the t table value is t dot inv dot 2t, where alpha and degrees of freedom are given. So margin of error is t times the standard error. Standard error is here. And then the limits are the sample mean minus margin of error, and then sample mean plus margin of error. Now we can give an interpretation that we are 95% confidence that the average difference in the task times will be between these 2 minutes. Now you see that 0 is within these 2 limits, so which means we can conclude that the difference is not significant. The difference is 0.